real content class today, so I'm kind of excited. This is Diane Spector. She is with Wank and Associates.
Wank Associates.
Wank Associates. There's no and. Wank Associates. Diane has taught hydrology in a variety of settings to a whole bunch of different audiences. This is one of the most important courses of the whole program because you have to understand how water and land work together. So I'm thrilled to have Diane teaching this. And I'm going to just give you as much time as you possibly can have. So I'm going to stop talking.
Thanks, Peggy. And it's great to see you all here tonight. And from someone who works with water resources and watersheds, thank you so much for volunteering your time and your resources to become master water stewards. Volunteers are really the keystone to really getting anything done. In part of my life, I happen to be chair of our neighborhood association on the neighborhood that I live in Minneapolis, and we could not do anything if we didn't have volunteers that were motivated and willing to put in the time and effort to make things happen within their communities. So just a little bit about me before we get started. I am a water resources planner and scientist at Wank Associates. We are environmental engineers. I work almost exclusively with watershed organizations, cities and counties, and other types of public sector organizations to manage their water resources. A lot of what I do is to help them analyze what's going on within their waters, within their watershed, plan for the future, and diagnose what type of issues there might be and come up with plans to improve and protect their water resources. So I spend a lot of time doing management plans and TMDLs and stream assessments and all kinds of cool stuff that very often I'm forced to go outside on a nice sunny summer day and like go out on a lake and collect aquatic vegetation. So if you can work it for that's your job, more power to you. What we're going to do today is an introduction. Hydrology can be, you can get a PhD in hydrology. We're not going to get a PhD in hydrology today. What we're going to do is cover some basic concepts. I'm going to give you a couple of tools for what you're going to need as a master water steward and introduce you to some other concepts and terminology so that as you're working as a water steward with other types of organizations or groups, and somebody mentions Atlas 14, you can respond not with a quizzical look on your face, but, oh, I know what Atlas 14 is. So you may not necessarily have to use it in your work as a water steward. Good to know. So our learning objectives, basically we're going to hit 4 learning objectives. So we're going to understand how we describe, calculate, and measure water and how it moves. We're going to understand the factors that influence how water moves and how that changes and shapes the land. And then finally, how those precipitation patterns are changing and how that may have an impact on how we manage our water resources in the future. So to get started, one of the things that we asked you to do as homework for today is to find an article or a posting on a website, something that had to do with water and flooding issues or something to do with hydrology. So I hope all of you did that because I'm going to ask one of you to volunteer to describe what you read, why that caught your attention, and how you think that's important. Do I have a volunteer? Go ahead. So did you read something that was helped you to understand that? Okay. One of the things we're going to talk about today is how that's measured and what kind of impact that has. I have another volunteer. Go ahead.
I'm interested in forecasting, so I looked up how various methods for forecasting of rain events.
Okay.
And then its relation to hydrology, which I guess is more in terms of impact on rivers.
Tell me one thing you learned.
Forecasts are either generated by quantity forecasting or by probabilities of
when we leave here today, you're going to understand how that's done and why. So, another volunteer? Go ahead.
I thought it was nice. So I wanted something that I didn't know. And I looked up and I found out that the U.S. Forest Service is starting to look at 3D modeling of cloud cover and estimate precipitation. So that was interesting. Another way to calculate, another way to predict, another model.
Did you know that there are things called montane forests, which are forests which are on the slopes of mountains that are actually in the clouds? Clouds condense on their leaves, then that runs off and runs downhill, and for a lot of locations, that's their primary source of water, is from the clouds that are condensing on the leaves. So, one more.
But that follows this as well, because I found an article about the U.S. Forest Service doing some monitoring in higher elevations in the Pacific Northwest. And they said that, well, years ago, all of their research was done in the lower lands. Precipitation, they found that wind was having a great effect on the amount of precipitation that was falling. And the only way they knew that is by going up to higher elevations to do the research. And now they're finding that wind patterns are changing precipitation levels dramatically. And that
Going up or down?
going down, well, it depends. It depends on the wind pattern. And that was then, I started doing more research about, well, how can a scientist actually accurately measure precipitation if they're dealing with something so uncontrolled as weather patterns or wind currents, which is what's happening now.
Well, that's an interesting thought. We won't be talking about that today, but I'd like to know more about that myself.
It confused me greatly.
One more. Over here.
Some people start off, but I found a webpage from environmental research, and it talked about warmer weather, and when there's warmer weather, there's more moisture in the air. And the fact was, for every degree of temperature, there's 7% more moisture in the air. But with every degree warmer, the rainfall was, the effect on the intensity of the rainfall is twice as much. So they said with every degree temperature warmed, there's a 14% more intense rainfall. So my questions were, do we see these changes in Minnesota or in Minneapolis? I mean, is there weather changes that create these issues? And then if so, if we are seeing more intense rainfall, how does that affect how you manage rain or the runoff from the rain?
Those are such great questions. We're going to talk about that towards the end of the evening tonight, because that is a really important topic right now, and there's not a lot of guidance on that. So hopefully keep that in the back of your mind, and kind of these issues that people brought up here, keep that in the back of your mind. As we dive right into here, I'll just start out by saying that I've taught hydrology to high school freshmen, so I think you'll be able to, by the end of today, consider yourselves not hydrology experts, but at least more knowledgeable about hydrology than what you were when you came in the door. So let's jump in. What is hydrology? It's the science of properties, distribution, and circulation of the waters of the earth. So what is precipitation? What are its properties? How does it move, both locally, and also how does it circulate around the world? Distribution, circulation, and properties. Why do we study it? Because water shapes the land, sometimes in really big ways. I think you're all familiar with the Grand Canyon. Sometimes water shapes the land in really, really intensely local ways. That creek didn't used to be as close to that house as it was. Luckily, they've got a canoe right there. Water influences where we live. Here's St. Anthony Falls in 1867. This is why Minneapolis is where it's at. This shaped Minneapolis and how it became a powerhouse at the turn of the 20th century. Literally a powerhouse. Why do we study hydrology? Because flowing water picks up stuff as it flows across the earth. There's a lot of stuff in that water. And finally, we study hydrology because this is the only water that we'll ever have. All of the water that ever has been or will be is currently on the earth. We're not getting any more. It's just moving. And sometimes it's moving to places where we can't get at it. Or it's changing in quality. So we can't do the same things that we used to do with it. Remember science class? Okay, the hydrologic cycle. So, I can't use the pointer, can I? Shoot. Okay, so here we've got that big dynamic circle of the hydrologic cycle. So we start out, we got clouds, right? What comes out of clouds? What's that term that we use for what comes out of clouds? Precipitation. Precipitation can come as rain, it can come as snow, or as some combination of the two. In hydrology, around these parts, we're mainly interested in rain. We're not oblivious to snow, but we're mainly interested in rain. If we were out west, we'd be mainly interested in snow and less interested in rain. Okay, what happens when water hits the land? Where does it go? There's multiple places it can go. Okay, when it goes into the soil, what's that called? I didn't hear you. Okay, infiltration. So when water goes into the top level of the soil, it's called infiltration. Sometimes that soil's got little cracks and things to allow it to go even deeper down and replenish our aquifers. What's the term for that process? What do we call that? Percolation, that's right. So if I had my little pointer here, I'd point to the difference between here, but on the left you can see the infiltration arrow. And the one on the right is the percolation arrow going down into that fractured rock layer, which is at the aquifer from which we're withdrawing drinking water. So some of it goes into the ground, some of it goes down into the aquifer. Where does the rest of it go? Overland. Okay. So it's going overland, and what do we call that term? Runoff. Okay. Runoff goes to where? Goes into surface waters. Okay. So it could be like in a lake reservoir, it could be in the ocean, it could be in a wetland, somewhere just on the surface. Once it's on the surface sitting there, if it's not going to groundwater, where is it going?
That would be evaporation.
Okay, there's evaporation. There's another process maybe you're not quite as familiar with. Does anybody know what that's called? And Jeff, you don't count. Good? When you're considering both processes, it's called evapotranspiration. Transpiration. Vegetation, when it takes up water, uses that in photosynthesis, releases the vapor up into the air. That's called transpiration. That water vapor is then available just like water vapor that evaporates off the surface. And that becomes what we together call ET, evapotranspiration. Goes back up into the clouds. It is, as we say, a cycle. Okay, does everybody remember all those terms? Those are going to be the most common terms that you're going to use. Infiltration, percolation, runoff, transpiration, evaporation, or ET. Everybody got that?
And what do you call it when humans use the water?
In interim use. Because they don't use it for long. Okay, Hydrology 101. These are the things that we're going to walk through. What is a watershed? How do we measure water? What influences how water moves? How does water impact the land? Are our precipitation patterns changing? What is a watershed? Anybody want to venture a guess? Or a definition? You're on the right track. It's the area of land that drains to a water resource. Right. So it's our convention to name our watersheds off of that water resource that it drains to. So if you're in the Minnehaha Creek watershed, everything in that area drains to Minnehaha Creek. right? If you're in the Lake Minnetonka direct subwatershed, everything in your watershed goes directly to Lake Minnetonka. This little funky looking leaf looking graphic is kind of a conceptualized diagram of a watershed. It's an area. It's got some sort of drainage ways. Those drainage ways could be streams, they could be swales, they could be storm sewers, they could be gutters. Any way that water can move, get connected and move downstream. We call it a dendritic pattern. So we've got our watershed with our drainage system all going down to that one point down at the bottom of the watershed. Sometimes we call that the pour point, P-O-U-R, the pour point of the watershed, because that's where the water pours out of the watershed. Watersheds can be small. The bottom. It's the bottom. It's where the water is leaving the system. Sometimes a watershed can be as small as your neighborhood. And that point where it's leaving the watershed is the storm sewer. Go ahead. Mm-hmm. You can also have a ground watershed. And a ground watershed is not necessarily the surface watershed. Wrap your heads around that. So what we're doing is right here, we're mainly concerned right now with that surface watershed. But from the bigger perspective, if you're the DNR trying to figure out what to do about White Bear Lake, you're interested in the ground watershed and how it intersects with the surface watershed as well. Okay? So we could have our neighborhood. It could be something. It could be something larger than that. It could be the Mississippi River watershed, which covers 40% of the United States. So here you've got the Mississippi River watershed. It's got some sub-watersheds to it, the Missouri, the Arkansas, the Ohio, the Tennessee. And then within each of those sub-watersheds, there are more sub-watersheds. You can drill down till you get to the very, very smallest unit of where water is running to. It's often defined by topography. And in an urban area, that topography might be, you know, here's the high point on the street, so that's the edge of my watershed, and one way it goes this way, and one way it goes that way. So this is Minnehaha Creek. Minnehaha Creek has got 11 sub-watersheds. The biggest one is what we call the Minnehaha Creek sub-watershed. That's everything from the Grays Bay Dam all the way down to the river. Oh, yeah, that's right. I forgot we could do that. So here we go. This guy right here. This is the Minnehaha Creek subwatershed. Then we got, you know, an area which goes directly to Lake Minnetonka. And then we've got all these smaller subwatersheds. We've got Gleason Lake. We've got Long Lake, Painter Creek, Dutch Lake, 6 Mile Creek, Lake Virginia, which includes Lake Minnewaska, Christmas Lake, is its own little subwatershed. So you've got 11 subwatersheds. And those are useful for doing hydrologic modeling to break them down into smaller units, and also for planning activities. If you've got a 180 square mile watershed, it's kind of hard to plan activities across the whole watershed in a meaningful way. But if you break it down into smaller and smaller units, now you can start having an area of land that you can kind of get your hands around. So if I want to do something about Christmas Lake, all I can do is just look at the Christmas Lake subwatershed and focus all my energies on Christmas Lake, right? Or if I define this as the little catchment subwatershed area in my neighborhood, then I can focus my efforts in that area, and then that define everything that I can do within that area then has an impact on what's coming out of the pour point of my subwatershed. You can break these down finer and finer and finer. I like to call these really small ones catchments. If you go to Europe, you'll find that instead of watersheds, they call them catchments. So I feel very cosmopolitan when I call these catchments. But this is an area of, there's Lake Harriet, and you can see the creek kind of running through kind of the center there. And all these little areas here are little neighborhood drainage areas. And some of them are bigger and some of them are smaller. But that helps you to define and focus efforts in that particular catchment area.
Those are created by the Public Works Department, or who defines all these things?
It depends on who's doing this work. For example, that's the kind of work that we do as consulting engineers, is by looking at the drainage system, you're looking at the topography and where the storm sewers are and the grade of the streets and things like that, and figuring out where those break points are. You know, if you're in a really hilly area, it's easy to figure out because you go to the top of the hill and water goes one way and then it goes the other way. But if you're in a nice flat city, it becomes a little bit more challenging to figure out the boundaries there. So, well, sometimes you got to go out and if it's really important, then you can go out and you can actually do a test. You can do a drainage test where you're just putting water down and seeing where it goes. Yes. Yep. So all of these subwatersheds on the upper watershed all go one way or another to Lake Minnetonka. And then Lake Minnetonka outlets to Grays Bay. So how do we measure water? See, sometimes you have to go out on a nice sunny day and just walk along a pretty little creek and take some water measurements. Bummer. There's one of my colleagues out there measuring the amount of dissolved oxygen in the stream. So the first thing we want to do is measure precipitation. We can measure precipitation with varying levels of specificity. We can put a little rain gauge in a cute little turtle in our backyard and just see how much rain we got in our backyard. We can go up, we can do this, these tipping buckets are pretty they're a pretty standard way of doing it. You can get them to varying levels of precipitation. Basically, the rain goes in through here, goes down the tube, and into this, goes into this tipping bucket, which is sitting on a pivot. So each one of those little triangle guys here is calibrated to hold a certain amount of water. So that might be calibrated to hold 0.05 inches of water, of rain. So when it gets to 0.05 inches of water, it pivots and it dumps the water, and then the other one then is available to fill up. And then there's a little device in there that counts just the number of times that it tips. That's why it's called a tipping bucket. And then you can walk up to it with your meter and just read off the number of times that it tipped, and that's how much rain you got. Or you could be the NOAA, the National Oceanography and Air Administration. I have trouble saying that for some odd reason. Otherwise, we'll just call it NOAA, and then I don't have to say it. So they have very, very precise rain gauges. This is a little excerpt of a figure that I took. If you're kind of a weather nerd, which I sense many of you here are, if you haven't been to the office of the state climatologist webpage, go spend some quality time there. It's full of all kinds of cool weather stuff. So this figure shows, if you can see all those little orange dots, those are all volunteer weather stations across the metro area, where volunteers have little backyard weather stations, and they're recording temperature and precipitation, and then they're reporting that to the state climatology office. So you see we've got a pretty extensive network throughout the metro area. The more data that we have, the more data that we have available to us to help forecast some of those trends. And we're going to learn about how you determine what the frequency return of a rain event is. More data, better predictions. NOAA also maintains what they call the National Climate Network. So they have this network across the country of really very precise weather stations. And then you can see the big telemetry unit there where they're returning that data real time to NOAA. And as I said earlier, around here we mostly are concerned with rain. We're less concerned with snow, but obviously out west, they're really concerned with snow and snowpack. It's very, very important to them that they know exactly how much snow they have, how much water content there is in that snow, and then that data then can be used to predict how much melting is going to occur in the spring and how much the reservoirs then can be filled up. So all those little bubbles on that map, those are all represent this network, which is called SNOWTEL, which I forgot what the acronym stands for, but it's about something about snow. And so each one of those is a station that looks kind of like that one in the inset there. It's a cleared off area. It's got a big pad on the ground. And that pad then is heated. And they can actually then record the amount of snow. And then when it melts, they can then record how much water comes off of that pad. And then that then becomes the density of the snow. So you probably can't read it because I can hardly read it, but this Moses Mountain station had a snow depth of 40 inches that was holding an 18.7 inches snow water equivalent. So that's pretty high. It's usually, you know what the rule of thumb is for rain to snow? 1 foot to 1 inch. Okay, so they've got a lot higher water content in their snow here because they've got about, well, I can't do the math, say 20 inches of rain to 40 inches of snow. Mm-hmm. And what NOAA does, this SNOWTEL is managed by the Natural Resources Conservation Service, but they all share data, obviously. What they do then is depending on the density of monitoring stations that they have, they might average it out, or it'll all become part of this very large, very detailed hydrologic model, where they may then define that catchment so detailed that they can then take into account those different stations and their different water, how much water is in the snow. So even though the stations may be relatively close together, they may have different water content, and then they can take that into account in their models as to what they're going to predict the amount of runoff coming from that is.
And Diane, snowpack is the story of it.
It's definitely. We have an office in Cheyenne, Wyoming. Water resources to them is very different than water resources to us. They're all about water rights, managing reservoirs, dealing with snowpack issues, dealing with those kinds of water reuse, things like that. That's where they get their water from. Okay. All right, now the math starts. So once we have our rain gauge system out in place, it's out in the world, we get a rain event, and we call them rain events because they're parties. We get a rain event, and we're looking at that rain event, and we are measuring it. We're measuring it over time. So this way of expressing that over time is something that's called a hydrograph. Nobody uses the word hydrograph in the real world. But this is called a hydrograph. Each one of those bars represents 1 hour. So you can see that when this rain event started, it started out pretty light. These are increments of 0.1 inch up the side here. So, maybe 0.05 inches in an hour. And it kind of stopped for a while, kind of stopped and started. And then, whoa, we got a 0.5 inch in an hour. The next hour got about 0.4 inches. kind of scaled back a little bit, stopped for a while, and then it rained again some more. So one thing to notice about this, well, what do you notice about this? Tell me what you notice about this rain event.
Had a couple big bursts.
A couple big bursts. What else? Starts and ends slowly. Good. Mm-hmm. And really the most obvious thing here is that it's not at a uniform rate, right? It starts and stops. Sometimes you get a whole bunch in 1 hour. Sometimes you get nothing, okay? That's one of the reasons why we look at it over time, because what we're interested in is not on average, but we want to know peaks. We want to know how much rain comes when it's coming down the fastest. So we're looking at this over time. So a really common time unit that we look at this is we look at it over 24 hours. So this rain event over 24 hours generated 3.85 inches of rain. We call that the rain depth. So in our rain event, our party, we received 3.85 inches of rain over 24 hours. But if we look at the most intense part of the rainfall, that's 6 hours, we got 1.55 inches of rain over that time. So when we talk about that this is not happening at a uniform rate across the 24 hours, or across the whole event, it's not even happening at a uniform rate across these smaller increments of time. Okay, so if we look at these in terms of a rate, we've got different peak rates. Okay, so that 3.85 inches over 24 hours, if you just divided that by 24 and said, well, this is how fast it's raining, you're getting 0.16 inches per hour. You have an awful lot of hours there where you're getting more than 0.16 inches. So if you looked at 0.16 and decided that I'm going to design a storm sewer or something to accommodate that, if you only accommodate that 0.16, you're going to flood somebody out because you've got a lot more rain coming down throughout your storm. If you look at the 6 hour, 1.55 inch, okay, that's 0.26 inches per hour. If you look at the 2 hours, and I didn't do a slide on it, but just those 2 hours where it was really coming down, we got 0.9 inches over 2 hours, that's 0.45 inches per hour. Big difference. So you've got different rates depending on what that different duration of time that you're interested in looking at. So what, if you were doing hydrologic modeling, which as a water steward you're probably not going to unless you get really, really interested in this and decide to get more into it, it's going to be very important to look at the duration of the rain and also the rate, because we have to figure out what's the best rate to design our infrastructure to. If we designed it to that 0.16, we're going to under-design it. If we design it to that 1 hour when it was raining at 0.5 inches per hour, we're probably going to over-design it. We have to find a happy medium. And that's kind of the art of hydrology. That's why people get PhDs in hydrology. Okay.
How does, like, they talk about, like in flood control,
Mm-hmm.
like looking for 100-year events?
Yep.
Is this similar then?
It is, and we're going to talk about that shortly. So, what I would like you to do now is in your notebook, we're going to have a pop quiz. Oh, saved by the question. Mm-hmm. There is no hard and fast rule. It all depends on what duration it is that you want to look at. Okay. So regulatorily, usually you're looking at 24 hours. So you're just looking for the 24-hour period where most of the rain seems to have occurred in, and calling that your event. All right, quick quiz. Get out your notebooks. You've got 1 minute. List the 3 things that we need to know about a rainfall event. The 3 things we need to know about a rainfall event. And when you're done, you can admire that photo that I found on the internet today.
That billboard is accurate. Jesus saved. Somebody needs to be saved.
It took me a minute when I first saw that picture. I went, is that an ad? Oh, no. Okay, pencils down. All right, what are the 3 things you need to know about a rainfall event? How much? Where? Duration? Rate. Okay. So we're going to say depth. For how much, we're going to say depth. Time, we're going to say duration. And for rate, we're going to call that intensity. Depth, duration, intensity.
What about location?
The location is wherever it is that you are. Okay. This photo, it said it was from the 1930s in the LA area. That's all I know about it. But I was just looking for photos of rain and flood. Okay. Speaking of, as we just were, about what rainfall events are we most interested in? What's a 100-year event? This is how we figure it out. We call those things, what's the return period for an event? The return period is calculated as 1 over the probability that something is going to happen. So an event that has a 1% chance of occurring in a year, 1 over 0.01, is a 100-year event. Funny you should ask. You take all the data that you possibly can get about, say, it's runoff in the stream by your house. Okay, so you're getting the peak. And if you've got a really long data record, you can look at the annual peak. So what's say you live by Minnehaha Creek. What's the fastest it's flowed every year? So let's say you've got 100 years of record, you got 100 data points of what the fastest it has flowed. You literally can put that in a spreadsheet, order it by the highest to lowest, and you can graph it on a probability graph, and it will show up. Then you can draw a line through it and say, that's my probability line. You know, that probability graph shows you, it's logarithmic, so you've got the 1 year, the 5 year, the 10 year, the 100 year. And if you want to know what the 100-year event is you go to 100 years and you go up to your the line that you drew on the graph, and that's what your 100-year event is. You can do that for stream flow. You can do that for precipitation. You can do that for discharge from a pipe. It's just a statistical analysis of the data that you have. How probable is that flow or that rain event going to occur?
So one of the other questions has to do with getting the data for that 100-year event. You're using a river mirror of looking at.
Right. Mm-hmm.
So now we're looking at how to shift the view forward because of climate change. And I was just talking to Met Council people who are working on water supply, and even in their numbers right now, they're not necessarily using the new numbers on steroid from when you look at recent rain events compared to past rain events, and also what's projected in the future. So how would you recommend us thinking about when somebody's designing for, like, let's say looking at a neighborhood and they're planning for a 100-year event? Well, if the 100-year events are coming every 10 years, then 3 years, and they really need to think differently about their pipes in this Edina neighborhood, or people's basements are going to be flooded out. So how should we think about using past data versus the future data?
Well, that's a great question. And actually, a couple years ago, I was at a conference in Atlanta, and there was an attempt made to by using some of those international climate change models to predict how rainfall patterns are going to change. And they were particularly interested in knowing if events were going to change in depth and duration, in frequency, and if they were going to physically change in location around the Atlanta area, because of course they're in the midst of their water shortage. So they wanted to know, should they build more reservoirs, and if so, where, and how should they size them based on how much rain could be expected in the future. It's a really difficult thing to do because of the assumptions that you have to make in your model. You can certainly do it. You can do what's called a sensitivity analysis and say, okay, I'm going to assume 10%. I'm going to run what my 100-year is right now, and then I'm going to increase that by 10% and see what comes out. And if that's significantly different, then I'm going to decide which number I'm going to use. But it's very subjective at this point because we don't have enough information about what's happening with weather patterns in order to really say definitively what to do. We'll talk about later about some of the observations that have been made, and then we'll talk about how we can take those into account as we're designing things. But yes, that's a very important thing to consider. In the back?
The article that I chose was the International Satellite It just seems like there's a ton more data.
Mm-hmm.
And so as a professional, what is your thought in this conversation? How do you see that changing?
It's a ton more data, but it's of short term. You know, what I said earlier about the more data, the better your numbers and the more confidence that you have in your numbers. We're looking at some precipitation records that are 80 to 100 years compared to, you know, maybe 5 or 10 years of this more intense data gathering that's going on since we're starting to observe some changes in climate. So I would feel more comfortable if we had a longer period of record with those changes in place to know exactly what it's going to do to precipitation and how we deal with it. Because right now, I can approximate that just like by saying, I'm just going to add 10% onto it and call it good. Because there's a lot of different things that can change, and we'll talk about some of these things. But you know, we talked looking at the shape of this hyetograph. One of the things that we're observing is that the shape of these hyetographs are changing. They're becoming more intense in the middle of the storm. Okay, so they're getting tighter in. So we're getting a lot more precipitation over short periods of time. So there's a lot of different bits and pieces that go into this, where we just need more data in order to feel more confident that we're able to really accurately model what's going on. You had your hand up?
Yeah. So in my hydrology class I took, they told us that when you say a 100-year event or a 2-year event, that's not saying that event's happening every 100 years or every 2 years. And I was wondering if you could explain a little more about why that terminology is there.
Well, the terminology is there because that's the way we used to think about things. Okay. It's just old words. Because it's easier for people to think of something as being, well, this is something that happens only once every 100 years, than it is to think this has got a 1% chance of happening. If you flip 100 pennies, you know you can come up with 10 heads in a row. Okay? You can have, in 100 years of record, you could have 100-year events 10 years in a row. That doesn't mean they're not 100 years events anymore. It just means that, you know, that happened. Now, if you get 10 100-year events in a row, you better go back and look at your probability analysis and make sure that your probability analysis is right, or see if something has changed. But again, it's if you're really thinking about it accurately, you're talking about probability and not, I don't have to worry about this because it rained really hard 2 years ago, therefore it won't rain hard again for 98 years. So here we've got a return period. The 100-year event, the 2-year event are common. What rainfall events are we interested in? This is something that I pulled off of, there it is, NOAA Atlas 14. NOAA recently went back and updated its precipitation frequency analyses, which had been last done in 1960, and incorporated about 40 more years of data, and updated the precipitation frequency depths.
But where though? What is that referred to? What location?
This particular location happens to be right here. One of the things that with this new Atlas, they call it Atlas 14 because that's what they call it being published. I don't know what Atlas 1 through 13 is, but Atlas 14 is the latest precipitation data. And one of the nice things that they did about that is they put it online. And because they had a much, much wider array of precipitation stations available to them, they can make much more accurate rainfall estimates and much more probability calculations. So you can go online, and it's actually a map-based server. So you can put a point on a map and say, here's my house. What's the 100-year, 24-hour event for my house? So we like to look at return frequencies, this 2, 10, and 100-year return frequency. And then we also look at different durations. For most work, we're looking at the 24-hour duration, but there are other smaller increments as well.
What's the relation with that? In forecasting, they use synoptic time. Like, did you measure the forecast at uniform times around the world? Is this related to that?
No, not really. It's based on recorded data, but they may not necessarily be synoptic. In other words, they may not necessarily be taken all at the same time. Because it's continuous because it might be raining over here one day, but 5 days later it's raining over there. So it's not at the same time.
And when these new numbers come out, then who in the state of Minnesota gets to tell all the engineers what they need to design for, like what the new things are?
Nobody gets to tell anybody anything because there's nobody in charge.
So why, if Dyna is designing pipes, they have to have some standard they have to design to, don't they?
Yes, and they're more than likely going to be changing from that study that was done in 1960, TP40, Technical Paper 40, has been supplanted. Everybody used TP40. It was just the standard. It's been supplanted by Atlas 14. So now most, whether it's a city or a watershed organization or MnDOT or other organizations, entities that do hydrologic modeling, they're moving, they're using Atlas 14. One of the things that changed about in Atlas 14 is, and this is not related to anything climate change, but just simply it reflects better data, is that these 100-year events changed dramatically. The 100-year event for the Twin Cities in TP40 is 5.9 inches. Based solely on having a longer period of record, this statistical analysis says now you better use 7.4 inches. Okay? So if you had, again, that's the power of having more data and longer period of record. If you're looking at something that's based on probability, those 1 and 2 year events happen a lot. But the 100-year, the 1% chance events don't happen very frequently. So the longer period of record you have, the better data you have, the more accurate this can be. Does that mean that everything that's been designed using the old 5.9 inches ought to come out of the ground and be replaced? No. But it does mean that in the future, as things are replaced, they should be using the new data and the new numbers. So when somebody says to you, did you use the Atlas 14 figures? You can say, yes, I know what Atlas 14 is. I would try. National Oceanography Administration. Thank you. Oceanic Atmospheric Administration. She sells seashells by the seashore. Okay. What other types of events are we interested in? You as water stewards are going to be real, it's good to know about these other events and these other precipitation data. But you as water stewards, you're really going to be interested in two events. One is just the 1-inch event. No probability associated with it, it's just getting 1 inch of rain. Something else we call the water quality event, which is a little bit more than that. Why are we interested in the 1% event? Or why are we interested in the water quality event? Well, these two graphs up here were done by a researcher named Dr. Robert Pitt, P-I-T-T, cool guy. Did a whole bunch of research in the city of Milwaukee. Went out and did a lot of precipitation measuring and runoff measuring and water quality analysis to try to determine in an intense urban area, when do we get rain events, what are the size of the rain events, and when are they taking, as we said, when water moves across the land, it picks up stuff. When it's picking up the pollutants, when is that happening? And what he was really interested in are those really small events, not the big gully washers, not the 7.4-inch 100-year events. He's interested in the really small events. Why? Because if you could read these numbers, you would see that a 1-inch rain, on this line right here is the cumulative rain count, about 95% of the rain events are 1 inch or less. 95% of all the rain events that we receive are 1 inch or less. Furthermore, look at this line right here. This is the accumulated volume of runoff. That's about 70%. So those 1-inch events convey about 70% of the total volume of runoff in a year. The majority of the water that runs off the land from those really small rain events. In Milwaukee, Milwaukee is very similar. So we can go to Atlas 14, the precipitation data server, and check it out. So that's where a lot of our water comes from. Now those graphs on the right there, you might be able to see that they're labeled SS for suspended solids, COD, carbonaceous oxygen demand, PO4, phosphate, and PB, must be lead. Okay. So when he was collecting these water samples, he's trying to determine which types of events carry the most pollutants. So have you heard of something called the first flush? Okay, some people here have heard about the first flush. First flush is that first water that rolls off the landscape. Picks up the most stuff. Washes the leaves and the grass clippings away, the garbage away, runs over the surface of the street, picks up all those little shreds of tires, picks up the sand, picks up the oils and things like that have accumulated on the roadway. That first flush has the worst water quality of runoff. That first flush happens in that first 1 inch. So in this particular case, he measured that this first 1 inch conveys about 70%. Why do I do that? It's about 70% of all the nutrients that head downstream to your river or your lake. 70% comes in that first inch of rain. If you want to go up to a little bit higher to that water quality event, that 1.3 inches, which I seem to have lost control of my cursor. Anyway, if you follow the red lines on the right side, you'll see that it's about 90%. we focus on these. You as water stewards are going to be focusing on these because that's where we're going to have the most water quality impact. Okay? For looking at the 1-inch event or at the larger water quality event, you're getting most of the volume, you're getting most of the pollutants. You're not ever going to be able to deal with those big gully washers, but you can sure have an impact on those smaller events. By having an impact on those smaller events, you can have a big impact on reducing the amount of pollutants that are going downstream. Mm-hmm. Well, and sometimes we get overly concerned with things like nutrients and sediment and things like that in our pollutants, but temperature, there is thermal pollution. If you're running rainwater over warmed pavement, that runoff then becomes warmer than what it was. When it discharges into a stream, just think of it's discharging into a trout stream. Okay, so you're discharging warm water into something that's supposed to be supporting cold water fishes, and you're suddenly raising the temperature of that stream. So that's a good point, we tend to get really focused in on things like nutrients, but there's lots of other things there that are of concern as well. So yeah, that is another thing that if you can prevent that first flush from happening, that extra warmed water from getting to the streams, you can help that biotic integrity as well. Yeah. Mm-hmm. Mm-hmm. This doesn't have anything to do with snowmelt. Snowmelt is its whole separate issue. But snowmelt is not going to be the event that's going to be carrying things like nutrients or sediments or lead to the water, to the receiving waters. It's going to be carrying chlorides, and it may be carrying things like sand and suspended solids. It's a different analysis, and the things that you do to try to avoid those downstream impacts are different than the things that you do in the summertime. So we're going to do just a couple of brief slides, and then we're going to do an exercise, and then we're going to take a break. Okay? So we've measured our water. We've got our depth. We've got our duration. We've got our intensity. We're disregarding that because we're just going to deal with the 1-inch storm on something. How do we convert precipitation into runoff? Anybody have an idea? Go ahead. Ooh, good. Kind of surface that it's hitting. Into the size. So how are we going to calculate runoff? Runoff is very simple. It's area times rainfall depth is volume. So here you've got a residential lot. You got a bunch of lawn there, it's green. You got a house with a roof on it. And you got a driveway that's paved. Okay? What happens to the drop of water that falls on the roof? Where does it go? Into the downspouts. If you're lucky, it's running off onto the roof, onto the lawn. If you're not so lucky, it's running off onto the driveway. Okay? Where does the water drop go that lands on the driveway? Into the street. Okay? So what do we call the type of surface that houses and driveways are? Impervious. What do we call the type of surface that the lawn is? Pervious. Okay. Oh, we're going to think really simple right now. Really simple. We're going to assume for this exercise that every drop of water that hits an area of green there is going to infiltrate into the ground. We're going to assume that every drop of water that lands in the house or on the driveway is going to run off. How do we calculate the runoff? Okay, we're going to take our 1 inch of rain. We're going to multiply it times the area of impervious surface. We have to convert that 1 inch into feet. That's why we've got the 1 foot over 12 inches. Okay? There's going to do the math, and you end up with 166.67 cubic feet. Remember, a cubic feet is a box, 1 foot on the side, right? A cubic foot of water weighs 7.5 gallons, or its volume is 7.5 gallons. So sometimes you might want to be thinking in terms of cubic feet. Sometimes you might want to be thinking in terms of gallons. By multiplying the area times the rainfall depth, making sure to convert that into feet, we can get the cubic feet, convert that to gallons. So if you're interested, for example, in dealing with the runoff from this particular property, and you're interested in dealing with that first 1 inch, the simple thing to do is just assume that anything that falls on the lawn is going to go in. Anything that falls on an impervious surface is going to run off. So all you need to know is the area of that impervious surface, multiply it times whatever your event depth that you're interested in, converting that to feet, then you get cubic feet, or you can then convert that to gallons. So in this particular house, assuming in that very simplistic way that we've got infiltration happening on the lawn and runoff happening on the impervious surface, we're generating about 1,250 gallons of water. It's a pretty manageable number. How big is a rain barrel? So it's still a lot of rain barrels. Now, let's say we needed to deal with the 1% chance event. That same house is generating over 9,000 gallons of runoff. So you can see that while we can deal with that 1,200 gallons, it's pretty darn difficult to deal with this much larger figure. It's about 9 times as much volume. Go ahead.
I was right, and I must have missed it. Up there, it's 2,000 square feet
Mm-hmm.
times 1 inch times 1 foot over 12 inches.
Yep.
1 foot over 12 inches is
That's how you're converting your units.
Okay.
So you're converting your 1 inch, right? Now, say you're interested in 2 inches, right? So you're going to divide 2 inches by 12 inches.
I missed the fact that it's a.
Yep. Okay. So the small practices which are oriented towards that 1 inch are going to be helpful towards dealing with that 70% of volume, that 90% of 1 inch or less rain events. It's not going to be very helpful for dealing with the rest of that volume. We just can't accommodate on site that amount of water.
And that's what you depend on the watershed.
Correct. That's why we're always going to have storm sewers. We're always going to have some way to convey those big events away from properties. But we can deal with the little events. So we're going to wind up this section by doing a little test. So grab a partner. You can work on this together. When you're done with this, you can take a break. And we're going to reconvene in 15 minutes. Can I put it on pause?
Yes.
It didn't go. It's refilled and gotten up and stretched your legs.
Great, good.
So come up and get your snacks, and then go. Then we'll get started again. Take some popcorn. Take some popcorn with you. We still got a few more people that are going to wander in, but let's get back together again. So, okay, did everybody have a chance to work their way through the terminology test? Yes. Did you all remember what they were? And the trick one that we didn't talk about? Okay, so let's just walk through them and just shout out what it is. Transpiration. Plant sweat. Oh, fabulous. Infiltration. Soak it in. Hydrograph. Hourly measurement of rain. Yep. Okay, a tipping bucket. Type of rain gauge. What's a 100-year event? 1% probability. What's a watershed? And what do you call the outlet of a watershed? The pour point. What's hydrology? Study of water and its property, distribution, and circulation. Runoff. That just moves along the surface of the world. What's a lake shed? That goes directly to a lake, right? So just like you can have a watershed going to a river or a stream, you can have a watershed going to a lake. And sometimes we just like to distinguish it from the bigger watershed by calling it a lake shed. You can have all kinds of sheds. You can have a ditch shed. You can have a pond shed. Finally, what's the return period? 1 over probability is the percent chance that something's going to happen. All right. Well, in this section of the class, we're going to talk about what influences how water moves and how runoff is generated. Now we're going through a lot of material. We're kind of going through it fast, so the presentation is going to be posted, and the video will be posted. You will probably want to go through it, especially before the next session we start talking about best management practices. Look, there's water going into a catch basin. And there's some garbage at the catch basin. All right, first thing that influences how water moves and how much runoff that there is soil. There's 3 major soil types. What are those 3 major soil types? What are the components? Clay, silt, and sand. Okay? What distinguishes those 3 different types of soil particle types? Oh, good. The space between them. The void spaces. Which type of soil has got the biggest void spaces? Sand does, okay? Sand has the largest particles, the most irregular particles, and the biggest void spaces. This guy over to the right here is the USDA soil triangle. It's a pretty standard kind of way of thinking about soil because you very rarely get soil that's entirely 100% any one of those 3 things. You usually get things that are a mix. So this triangle shows it's got clay up on top and it's got sand over to one side and it's got silt over to the other side. And it just shows all the different types of ways that they could mix. Like you could have silty clay loam, you can have loamy clay silt, you could have silty clay sandy clay, and it all depends on what percent of those different soil particle types are in your actual soil. So in this USDA soil triangle, they very helpfully pointed out kind of what we like to see. This nice loamy soil right in here in the middle, which is 40% silt, 40% sand, 20% clay. Nice mix. Lots of different particle sizes. It's got a nice amount of sand in it, so you got some pore spaces in there. It's got some smaller particles to kind of hold it together. Does anybody know how, if you're in the field, you're out there, you're just kind of walking along, and you say to yourself, I wonder what kind of soil that is. What's a quick and easy way to do that out in the field? You get a fistful, mix a little water in there, kind of make a ball out of it. So you got this ball of soil in your hand. You take your thumb and you push it. And you try to make a ribbon. If you got a lot of clay content, you'll make a ribbon. It'll be just like clay. The longer the ribbon, the more clay you have. If you can't make a ribbon, you've got a really small clay content. How do you tell if you've got a lot of sand in your soil, in your handful of sand? It's gritty. You can actually rub your hand and you can feel them. If you've got a lot of sand, you can look at it and you can see the sand. So if you don't have a soil test telling you exactly what kind of soil you have, that's kind of a quick way of finding out kind of generally where on the soil triangle you are.
And there's a website that'll tell you the soils underneath all 10 counties.
Yes, there is, and we'll see a picture of that. Yes. Yep. Yep. If you get, you're out there and you've got kind of like this nice, good kind of brown, black soil, that's usually pretty loamy. So the reason why we care about what type of particles are in the soil is because those different particles can infiltrate at different rates. So if you've got a lot of sand and you've got a lot of void spaces, you can run a lot of water through there because there's a lot of storage in the sand. It can dissipate very, very quickly. If you're up in the northern part of the metro area or up north of Anoka and you're on the Anoka sand plain, you have stormwater ponds, they can't keep water in them because it just infiltrates so fast. Silt, you get more silt in there, those smaller particles, they're starting to have fewer void spaces, or maybe you've got more silt in your mix and they're kind of filling up some of those void spaces around the sand particles. You've got less infiltration. If you've got very heavy soils, very clayey soils, those are really, really tiny spaces between those particles. You're not going to get very much infiltration out of that. One of the terms that you will encounter in your journey as water stewards is hydrologic soil group, also called HSG. The hydrologic soil group designation from the NRCS, the Natural Resources Conservation Service, which is the successor organization to the Soil Conservation Service, which was founded right after the Dust Bowl when everyone decided, oh, we ought to be paying attention to our soils. So we've got these four general classifications, A, B, C, and D. A is the sandiest type of soil, going down to D, which is the most clay soil. So it's an easy shorthand way of describing the type of soil you have. So you've got kind of like that nice kind of good gardening soil that's usually a type B soil. You've got really sandy soil, you say, yeah, it's an A soil. If you've got really terrible, heavy clay soils, they're D soils. It's just a nice little way of thinking about what type of soils and their potential to infiltrate. There is such a thing as the county soil survey, and you can go online and anywhere in the United States where the soil survey has been done, which is most of the United States, and pull up information about the soils in that area. This is a figure, this is one that I made, showing a corner of, where is that? It's 494 and 394, yep. So what you've got here is the areas that are, those couple little areas there that are bright red, those are areas of sandy type A soil. The areas that are in that light green are clay, really tight soils. You tend to find those in areas that are currently wetlands or they may have been wetlands in the past. Then that kind of buff color in the background are soils that are generally B soils. And everything that's kind of hatched are these funky in-between types of soils. We call them dual designation soils. So you'll see, if you look at the legend, you've got A/D or B/D. It means that when the soil is dry, it acts like, for example, a B soil, which means it infiltrates pretty good. But when the soil is wet, it just either it clams up and it doesn't infiltrate very well, or maybe there's something like there's a high water table in the area, so that when the water table is high, you just can't get as much infiltration. So if you've got just a plain old B soil, you've got pretty good infiltrating soil, or A soil. If you've got one that's got a dual designation, then it's going to be more problematic, to infiltrate in that area. If you've got a C or a D soil, then you're probably going to have to amend your soils in order to get any type of really useful infiltration out of it. This is very, I don't want to say high level, but this is done on a regional type of scale. In practice, you're always going to want to look at the soils that are specific to the site that you're looking at. You should never rely on the soil survey to design something, for example, like a rain garden or something. You should always look at the soils, and you'll be learning later on in this course how to do that if you don't already know. But this will help you understand, you know, if you're kind of in one of those green areas, you're going to know right away that it might be pretty difficult to really get any infiltration, you know, get some rain gardens done in this particular area.
Is there a way of knowing if the soil is underground is contaminated, where you don't really want to infiltrate water through contaminated soil?
The only way that you could really find that out would be either to dig down into it and, you know, do the smell test, or if you can go online onto the MPCA's website, and they've got something which is called What's in My Neighborhood. And the What's in My Neighborhood is a map-based application where you can zoom in on your neighborhood, and on there they will depict everywhere where there's been a leaking underground storage tank, an old dump site, a leakage of some sort, everything that they know about. So you can see whether that's something that might be present in your area. They don't necessarily know about everything. That's why you might need to know, someone might need to tell you, hey, when I lived here 40 years ago, there was a gas station on that corner. And, you know, maybe there might be some contamination of the soils there. And nobody's ever really looked into it. The MPCA, the Minnesota Pollution Control Agency. It's called What's in My Neighborhood.
So if you've got neighborhoods where, you know, it probably was a wetland, but of course it's been developed now.
Mm-hmm.
So I think what you're saying, and maybe the map shows too, there's very clay-like soil. So are you just saying really the chances of mitigating runoff is harder?
It's harder. It's not impossible. Even if you've got really heavy clay soils, you can still amend the soils. Just the practice of planting deep-rooted native vegetation will, over time, change the nature of that soil. It will make it more porous. As all those roots are, you know, moving down deeply into the ground, and they're making those channels in the soil, and the roots die off, and more roots grow. They're leaving these little these channels. So the soil actually becomes more porous over time. So just because you might be in an area of D soil, doesn't mean you can't do infiltration. It just means you might need to be a little bit more clever about how you do it. This is out of the state stormwater manual. Again, if you just wanted to conceptualize a particular site, and you knew generally what type of soils that you had. The state stormwater manual has some average infiltration rates. So if you've got really well-graded gravel or gravel with sand type A soils, the average infiltration rate is 1.63 inches per hour. So you've got kind of general, nice, loamy, silty sand type of soil, 0.6 inches per hour. Again, from just a very general perspective, it gives you an idea of what you might be able to achieve. You're always going to design based on what you measure in the field. So what this is doing is this is giving you something to plan from. This is from the state stormwater manual. It is online. You can look up the MPCA State Stormwater Manual, and they have a wiki that includes tons of information that you'll be learning more about in some of the later sessions.
That 1.63 inches per hour per square, what's the surface area or
Again, it assumes that it's uniform across an entire area. Now, we all know that's not the case. That's why you always design based on what you actually measure in the field. But again, if you're just doing some general, what kind of infiltration might I be able to get in this area? I've got type B soils. Let's start out by assuming we're going to get a rate of 0.6 inches per hour. And when it comes time to actually designing it, we're going to go out and we're going to do our infiltration test and actually measure what that rate really is. What's another factor that impacts how much water can be infiltrated into the ground versus what ends up not being able to be infiltrated and running off? We talked about it a little bit earlier, and that's compaction. Over time, even soils that, just out on your lawn, where you do nothing more than walk over them when you're mowing your lawn, over time, soils will become more compacted. They will lose their infiltratability, their porosity. The number one reason soils get compacted is because equipment drives over it. So if you've got developments that are happening and they're going in and they've got the big machines and they're doing their big grading, and then they're coming in and they're doing their fine grading, and then they're driving over it to build the houses, and they're driving over again to lay the sod, they're compacting the soil and compacting the soil and compacting the soil. And then they wonder why their sod won't grow, because they put it over concrete. Okay? So compaction is the enemy of infiltration. The only way to deal with that is to actually decompact it by using a type of equipment that can then just like drag a tine over it, or if you're in a smaller area, you can do it by hand just by using a spade or some other type of tool. So we have the type of soil, how much is compacted, and then we kind of talked a little bit earlier, I think, about slope and roughness. Slope has a big influence on runoff, both how much runs off and how fast it gets. And that's one thing that we haven't talked about yet, is how fast runoff occurs. Okay? So here we've got two watersheds the same size. They have the same length of stream running through them. One of them is kind of hilly or mountainous. One of them is maybe slightly rolling. Okay? 30% basin slope, 5% basin slope. So you can see that on this particular slide right here, they both start out, the starting point for most remote runoff in the basin is way up on the top of the basin. Considering the same amount of time the water gets to the stream gauge down at the pour point of the watershed, well before it gets to the pour point on the less sloped basin. We call that the time of concentration. How long does it take the water to get to, from the farthest point to the pour point, the point that you're interested in? That's the time of concentration. So you've got these slopes. So it's getting there faster. Because it's getting there faster, it doesn't have as much time to soak into the ground. And you're just getting more runoff, and it's getting there faster. So on these highly sloped watersheds, more and faster. On these lesser sloped ones, you've got time for more infiltration to occur, and it's not moving as fast through the stream. So it's the slope and the roughness. Lastly, this is something that's really important, something that we call directly connected impervious area. I didn't make this graphic. I would have made it less sloppy, but I think you can kind of make out the fact that that's some streets and a cul-de-sac and then some houses around it. And all that purple area is impervious area. And it's all impervious area that's what we call directly connected. It's impervious area that runs onto impervious area. So the roofs are draining to the driveways are draining to the streets are draining to other streets. We've connected up all that impervious surface. We've made it nice and smooth and nice and impervious. The water just runs right off and whooshes down to wherever it is, that collection point in that neighborhood. So if you've got a lot of directly connected impervious area, you will get more runoff, you will get faster runoff than if you've got disconnected impervious surface. You can have impervious surface that you're directing the runoff onto a pervious area. You're running your downspout onto the lawn. You're running your parking lot into a drainage swale and allowing it to infiltrate. So you've still got impervious surface, you're just not connecting it up. So whether or not it's connected is something that's important to how much runoff you're going to get. Oh, I didn't give you a cute, no, I didn't give you a picture. Quick quiz. This is one's by yourself. We just went over some factors influencing runoff and how water moves. So I want you to list at least 4 factors that influence runoff and how water moves. And then I want you to circle the one which is most important in urban areas. Okay, time's up. 4 factors. Somebody shout out one. Soil type, slope, compaction, impervious connectedness. Which is the most important in an urban area? Impervious connected. All right. So why do we care about runoff? Because runoff influences land. This is a really, really famous graphic. So famous, I didn't even have to put the source on the bottom. What happens to infiltration and runoff as development occurs from natural ground cover all the way to a highly urbanized area of 75 to 100% impervious cover? As you're developing, you're changing where water is going to. So as you slowly add more impervious surface, but you're still having some vegetation and tree cover, you're still getting evapotranspiration. But what you're getting is you're starting to get more runoff, you're getting less infiltration. As you start getting down to the bottom, 35 to 50% impervious surface, to get to that impervious surface, now you've taken out all the trees. You don't have very much green space. You're getting a lot less evapotranspiration. You've got all that hard cover, so you're getting less infiltration, especially to the deep aquifers. And as you're then getting to the most developed situation, you don't have that transpiration component in there. You're still getting evaporation because you've still got water landing on those flat surfaces where it can evaporate. But now you've gone from 10% runoff to 55% runoff just by changing your land cover. You've decreased what's going into your shallow and deep aquifers. It used to be 50%. Now you've got 15% of the rain that falls is going down into the aquifers. You've changed where that water goes. It's not going into the ground and into the aquifers anymore. It's going into the lakes and streams and rivers. Okay. Remember I told you that nobody uses hydrograph in the real world? Everybody uses hydrograph. A hydrograph shows the movement of water during and after precipitation. So this is just kind of a general schematic of a hydrograph. Hydrograph kind of has 2 components to it. One is precipitation. So you'll see those blue bars are precipitation. Sometimes you'll see a hydrograph where the bars are hanging from the top axis. But it shows you get some rainfall, and then that rainfall starts running off the land, and going towards your storm sewer or your stream or wherever it's going. So let's say this is Minnehaha Creek. So that runoff starts going into the storm sewer, runs through the storm sewer, starts hitting the creek. The creek starts rising to a certain point where it hits a peak, where it's running at its peak discharge. Once it's done that, the water, the water that has traveled from the furthest point in the watershed to the pour points, you're not getting any more water getting into your conveyance system. So you're not putting new water into the stream anymore. So it's starting then the flow is starting to fall. The amount of water in the creek is starting to fall. We have our rising limb, our peak, and our falling limb. And that amount of time between when you get the peak precipitation and when you get the peak discharge, whether it's in the stream or in your storm sewer or wherever, that's called the lag time. Okay? So your hydrograph has got rising limb, peak discharge, falling limb, lag time, precipitation. What do you think happens to this hydrograph when you move from natural ground cover down to the more impervious surface? Good. Lag time decreases. Anything else decrease or change about it? Okay. Passage of time. Here you've got precipitation. Comparing the blue and the red. The red is the pre-urbanized. Blue is the urbanized. Your lag time has decreased significantly. Your rising limb and your peak has decreased in time very substantially, right? You're getting to your peak much faster, and you're getting to a much higher peak discharge. So, whereas before you had kind of just a nice steady increase, now you've got a really fast increase, and then it goes down again really fast too. So don't neglect the falling limb here as well. On the pre-urban, you've got a nice, long, shallow falling limb. The urbanized one, you've got a really short, fast one. We call that a stream being flashy. And it's flashy because it rises up really fast and then it discharges through really fast. And those hydrographs for events are compared to the other hydrograph that you see on this here, which is called the stream base flow. That's that water that's always in the stream. It's coming from groundwater. There's always some water that just comes from groundwater in the stream. We call that the base flow. When it hasn't been raining, that's the discharge in the stream. We care about those changes in the hydrograph because those changes in the hydrograph change the character of streams. I'll show you what I mean. Here's a nice bucolic stream. This is in a nice undeveloped area. You'd want to picnic on the banks there, kind of hang out, maybe take off your shoes and wade in it. You'd expect to see lots of wildlife, look in the water, see some fishies, some frogs, some minnows. This is the same stream downstream through a city. Exact same stream, only now all the storm sewers in the city are being discharged into the stream. So you've got two things happening here. One is all of a sudden it's conveying a whole bunch of water really fast, and that velocity, that sheer velocity, is eating away at the banks of the stream. So those banks are falling in, it's making the stream wider and wider, it's digging the stream down, so it's getting deeper and deeper. And because that, as it's getting wider and wider, the other thing that's happening on the stream is it's getting shallower and shallower. So it's carrying the same amount of water, but as it's getting wider and wider, it's getting shallower and shallower. Which means that at a certain point, there's just not going to be enough water in there for fish and other aquatic organisms to survive. So, hydrological impacts of development of water resources is that urban runoff tends to make streams much more flashy. They rise up really fast, and then they discharge really fast. This is Shingle Creek up in Brooklyn Park. I happened to get a 2-year event over 3 hours. So this is the stream kind of at the peak of the rain. This is just upstream a little bit 2 hours later. So you can see that line of debris on the bank right there. Actually, that's debris from the chips on this playground over here. Whoop. Gee, you know, if I use that and I press down on it, it shifts the slide. So, and you can see the discoloration of the vegetation on the other side. That stream popped up almost 4 feet, and then went back down over the course of a couple of hours. And look at what a beautiful day it was then, too. The Shingle Creek watershed. The whole metro area is organized into watersheds. And some of them are organized as watershed districts, and some of them are organized as watershed management organizations. That one happens to be a watershed management organization. So.
Yeah, I came down Rice Creek, and it seemed to have a lot of wildlife. So I'm wondering, does Rice Creek have? It must be much less urbanized or something.
It is, and it's a much larger watershed too. It also has a lot more things like wetlands up in the watershed that serve to hold water.
In a way, though, wasn't that helpful because it looks like homes were not affected and quickly drained away? Was that the purpose of that creek, or was that a natural?
This is a natural stream.
Slope, was that ever designed to be such to give some temporary capacity?
Yeah, this was actually reconstructed. Before this reconstruction occurred, it looked a lot like that one, only deeper. And it had very tall, straight banks, vertical banks. So when this project was done, this was completed maybe about 4 or 5 years ago, they cut those banks back and then had a combination of vegetation, and you can see there's some riprap down there around the curve there, to stabilize it a little bit more, but also that sloping the stream back then provides for that storage. So when the water rises up, it's got somewhere to go. And yes, they did deliberately then, yeah. So everything should be above that peak elevation of the creek. So they built that in, but they had the data to do that. And when that redevelopment occurred, they knew that where they needed to put the buildings and stuff so that they would stay above that. Yep. The other thing that it does is decrease stream base flow. So remember that line down the bottom of the hydrograph was base flow? Okay, so where does base flow in a stream come from, do you think? It comes from groundwater. Where does the groundwater come from?
Surface.
From where from the surface? Infiltration. What happens when you create a whole bunch of impervious surface? No more infiltration and recharge. So then where's a stream supposed to get its water from? Huh? That's Shingle Creek, upstream of that last shot that we saw. And that's in August. I can tell you there aren't any fish in that stream. We did see some bunnies, though. So, if you're familiar with Minnehaha Creek, you know that when the Grays Bay Dam gets closed off and it gets further into the summer, that the base flow in the creek is very often so low that you can't canoe in it anymore. Same problem. So, you got urban runoff and flashiness, decrease in stream base flow. Where do wetlands get their water from? Runoff and from groundwater. Same problem. If you're not infiltrating as much, you don't have as much water going into the wetlands. What happens to your streams when you have flashy base flow? The banks fall apart. It's even worse in agricultural areas where the cows have free access to the stream and they can then further trample the banks. That's in Davenport, Iowa. Jeff remembers that one. So this is Duck Creek, which is a stream that bisects Davenport east to west. We thought this was, because upstream was just some agricultural area, we thought this was going to be a nice little stream, and it turns out it had 12-foot banks, which I don't know if it really comes through in this photo, but the banks kind of look like this. And there's poor Jeff in there pounding in. We measure what's called lateral rescission. You take rebar and you pound it into the bank horizontally, and you measure how much is exposed, and then you come back a year later and you measure how much is exposed. And he's there pounding, oh, hello, pounding, I'm really excited, pounding rebar into that bank, looking up at this overhanging huge mountain of soil there. And he was pretty darn nervous. That's a chunk that fell off. That it just happens to be downstream of agriculture. Duck Creek is like this, and even worse in some places as you get further into the city. The only thing that's kind of a saving grace for Davenport is that they rely more on channels and streams to convey their runoff than they do storm sewers. So it's slower to get there to the stream. Storm sewers can discharge their runoff really fast. So, yeah, I mean, it's like this. It could be worse. And what's nice about Davenport is, except for a little spot in the most upstream part within the city, it's all publicly owned, so it's all parkland. This runs through parkland, and then there's trails right up against it. So they're kind of nervous about these banks. Some of these have like trails right next to these falling down banks. Well, the first thing that you would do would be to re-slope the banks so that they're sloping. Instead of sloping like this, they're sloping like this. The second thing you can do is, depending on the velocity of the water that you have to deal with and what's called the shear stress, there are different things you can do. And surprisingly, something as simple as planting willows on the bank, planting live stakes, can go a long ways towards stabilizing the soil. One of the problems that they had in Davenport, because I said, it's going through park, nice lawns going right up to the very crumbling edge of the stream bank. So do you see any like long-rooted native vegetation on those banks? A little bit here and there, but basically it's grassland. So just planting the right vegetation, and you might in some particular cases have to do 2 or 3 rows of riprap right at the toe just to kind of stabilize it. But you can do an awful lot with native vegetation.
Farmers about the drain tile.
Yeah. So anyway. All right, another quick quiz. You can work with your partner. All right. How would you reduce the impacts of urbanization on our lakes, streams, and wetlands, and what changes would you make to the landscape to do that? So we looked at how the changed landscape has an impact. How can you go back and retrofit or change the landscape in order to try to mitigate those issues? Okay, work together with your partner. Let's work until 8:15, and then we're going to close out with a discussion about the changing climate. Okay, let's go around the room, and we'll just go up and down the tables, and you can discuss with the class your ideas, your thoughts for impacting or reducing the impacts of urbanization on water resources. Start all the way in the back. Okay. Anybody have any questions for the team back here? I'm sorry I don't know your names. I'll just point at people. Okay.
How would you then to, so you, to really do this railroad bed? Where you getting, who are you asking to do it? Right. But theoretically, where is the source of, funding coming
It's Wisconsin, and it just, I don't know, but they moved their town, so my guess is, oh. I don't know, but they've moved the town, so there is flood mitigation. There's gotta be money around, but I don't know, cause it's not my project really, we just talked about it.
Okay. Well, why don't we move on to the next team then? How about the two here on this side? Or wherever your team is here.
Sure. We just came up with some bullet points. One was to try to send impervious areas, water from impervious areas onto areas where it can percolate, like redirecting downspouts.
And what do we call that? Class? What are we doing to our impervious surface? We're disconnecting it. There you go.
Yeah. We talked about doing that on a bigger scale with disconnecting big impervious areas one way or another.
Okay. And how big of a scale would you go? Like parking lots, streets, and more? Okay. Okay.
Whatever we could get away with.
Okay.
We talked about planting trees to minimize compaction, and we kind of, as an offshoot, thought about new developments when they take all the trees out. Maybe they should leave as many in as they can.
Good thought.
We talked about collection points to slow down runoff, particularly where there's a lot of slope.
So collection points, are you thinking like ponds or
Yeah,
things like that?
ponds.
Okay.
Yeah. Talked about using more permeable materials wherever possible, like a brick driveway instead of a paved driveway. And we also, after listening to the people behind us, said we should increase awareness, and generally that could help reduce the amount of runoff.
Okay. All good suggestions. Any
Okay,
questions?
he took
or-
all of ours.
You're going to find there's a lot of duplication, but feel free to duplicate because y'all might have a little different take on it. So.
So we talked about native deep-rooted vegetation and increasing that, especially given your last comment about the willow staking. Breaking up pervious connections as much as possible, that was kind of already mentioned. And really focusing on those steep areas and slowing flow on those, because that seems to be an area where you can make more of an impact. And then re-engineering stream banks to decrease slope, if that's possible. And she was with.
Anybody have any questions for the team at table 2? No, if not, let's go up to table 3 here.
Increase infiltration. Increase infiltration. Decrease the non-compacted or increase non-compacted green space. Rain gardens, decompacting compacted soil. Decreasing impervious surface area along the lines of what we heard already in terms of pervious surface area alternatives. Reshaping of river stream banks, planting trees, green roofs, downspout disconnects, native species plants, deep roots like we heard already for riverbanks.
Okay. Kind of a whole lot of actions. What do you think would be to have the most impact?
Direct leak, the directly connected impervious areas, somehow disconnecting those directly connected
Okay.
impervious areas.
Okay.
Sure. One of the issues that I've noticed is that in remodeling neighborhoods, and so we kind of talked about maybe there should be more thought given to the house, the footprint, driveway footprint versus the open spaces. I've got a friend of mine who's complaining that a 3-car garage went up in their neighbor's backyard, and she's already said, "Where's the water going to go?"
Mm-hmm.
So things like that as communities are redeveloping, especially along Minnehaha Creek. But again, we talked about native plantings, sloping, creating slopes and swales to slow down water, redirecting or containing water. Again, maybe it's using ponds and other landscaping, shade trees, willow trees, stabilizing shorelines, riprap, and amending soil types to, again, increase filtration, and perhaps using French drains and things like that.
Oh, just generally creating more green space.
Okay.
Just both, taking away the impervious connections as well, but the building of green spaces to try to both cool urban centers and to redirect the transpiration that it involves with living plants.
Yeah, that's a good point. It's cooling not only the runoff, but also the air itself. And at least in my opinion, it's always best to get as many positive impacts from what you're doing as possible in order to maximize the benefit that you're getting from the resources that you're expending. So the more ecological benefits that you can get from something, the better. You brought up something that we haven't really talked about before, and that is there are some communities that have established a maximum amount of your lot that can be covered by an impervious surface. And there is already a requirement in what's called the shoreland management area that is within a regulated stream or lake, and that minimizes, it's an even smaller percent of that land area that can be covered by impervious surface. But there are many communities that don't. So that is something to think about, is looking at potential regulatory requirements that limit how much impervious surface you can have. Mm-hmm. Right. Well, it's just changing the way that the paradigm, changing of what should be considered an acceptable way that things look, changing the aesthetic. Yeah. You have a question before we move on? Well, and again, it's something to look at the city ordinances and whether or not the city actually has a shoreland management ordinance. I would suspect Mound does have a shoreland management ordinance where there are certain very specific regulations about what you can and can't do within that shoreland management zone area. They may have some properties that are grandfathered in that don't have to follow necessarily all those, or they may get a variance. One of the things that we find, especially in outstate Minnesota, is that the township boards are happy to give you a variance. So it's focusing efforts on educating people about why that is, what the negative impacts of continuing business as usual is, and why it would be important to change the way that you do things. And you have to express it in terms that they can understand. You have to be able to, that's going to be part of your jobs as water stewards, is to educate people as to why they should change the way that they do things. What kind of public benefit is there, and why should they care? So part of that might be persuading the city council and the planning commission to revise development ordinances.
Yeah, with our group, we were able to hear from Linda, or Scotty, she lives on a little lake called St. Joe's Lake is in, what is that? Chanhassen, and it has a A quality rating because it has wetlands all around the lake and no pervious surface going into it, and so they have really good water quality and a lot of good fish and everything, and so that was a positive example. We mentioned a lot of the other ideas everybody had in terms of putting in rain gardens and disconnecting pervious areas. One of the things I wanted to mention is that we think of our roads as being a permanent fixture, but they're being updated every 40 years or something. And so part of the project, I work for the Alliance for Sustainability, and we're encouraging cities to adopt a living street policy where they watch out for walking and biking, but they also look at how to capture more stormwater when reconstructing streets. So if any would like to join us, we're going to have an educational event for people in the Edina Morningside neighborhood on March 16th, where they can begin to look at requesting rain gardens when their streets are being redone. And so anyway, that's something they're developing right now in Edina, but if your city would like to create a living streets policy, you could talk with me and we can get you resources like the city of Maplewood that has a really great policy, so that it becomes automatic when you're redoing the streets that you re-engineer to capture more stormwater.
Good ideas. Any questions? Otherwise, see Sean.
Work with the city to implement that then?
Well, yeah, it would be something officially adopted by your city council. So the Alliance for Sustainability is using a number of West Metro cities to think about this. Like St. Louis Park has a new environmental commission, and Edina has right now a Living Streets committee working on this whole thing.
We talked fairly generally about ways to increase pervious surfaces and decrease increase oh boy, where am I going now? We want more infiltration to impervious surfaces. That's what we want. And but I was kind of remembering back to when people were first proposing around Lake Harriet and Lake Calhoun that we needed to stop all the rainwater, the stormwater from draining straight into the lake, and they reintroduced sort of a wetland by Calhoun and large rain ponds by Lake Harriet, and I don't even remember how far that was back, but I think that was sort of an outrageous idea to a lot of people. But I suspect that it has had a very positive effect. So things of that nature, and of course, planting native plants to increase infiltration too.
Any questions or comments? Okay, let's continue to move along. Somebody's got to do it.
Yeah. I guess pretty much to add on to what everyone else has been saying, we wanted to set up better riparian zones around the rivers and streams that add to the watershed. Because
And let's hold right there. Does everybody know what a riparian zone is? Okay, can you define what a riparian zone is?
it's the area that's like along like a stream bank or river. It's the area right adjacent to that land. All right, and so because I think the biggest impacts that we, or at least I thought, was like the velocity at which it's coming down from urban areas, and then also the green spaces that it can infiltrate. So those would kind of take care of both of those. You wanna add?
Yep.
Can you use the word buffer zone to replace riparian zone any times, or is it a totally different? Because in agricultural areas, don't they talk about buffer zones?
Right. And the question is, are buffer zones and riparian zones the same thing? They're related. The riparian zone is, it's adjacent to a water. So it would be a stream or a lake or sometimes a wetland can be considered, the area next to it could be a riparian zone. A buffer can be adjacent to really anything. But in water resources, we use buffers to mean an area between a developed land use and a water. So very often those buffers are in the riparian zone. So.
I can add a couple more things. All right. I also mentioned that when I was in Michigan, there was a town that was a restoration site. So between the sidewalk and the road, they had the whole strip was rain gardens, and they were required to be rain gardens. And then also when I was at Bethel, up to some of the dorms, instead of having the pavement, they had pavers. So pavers are also something you can do.
We basically talked mostly about the same thing, how to break up impervious connectivity. One thing, like in cities, we talked about adding green roofs to capture more rain from rain events. We also talked about minimizing use of blacktop because one thing that I found disturbing is the Minneapolis Park Board. They seem to be replacing all the bike paths and sidewalks with more blacktop, and if they would use more pervious surfaces, that would help. But we realized that that's probably financially unfeasible. So the issue of who pays for this came up. You know, it's great to talk about these things, but ultimately there's a financial cost for it. So who?
And that's a really good point there, because a lot of the things that we've talked about here differ in scale. Some of them are, you know, on a lot scale, and some of them are talking about a neighborhood or even a community scale. So part of the analysis that would go into determining what you can do and what you should do is how much is it going to cost, who's going to pay for it, how cost effective is that practice going to be. So obviously, whether you're spending public money or your own money, you want to be able to get the highest benefit for what you're spending. And part of, an important part of any analysis about what it is that you actually do is, are you doing the best and most cost-effective thing that you can do? Like you said, it'd be really nice to use pervious pavement on the trails and parking lots and wherever you can. Pervious pavement is much more expensive than traditional asphalt. So are there ways that you can use that judiciously and get a benefit from it, but not have to undergo that entire expense of putting it everywhere? So that's part of the analysis.
I was just wondering if pervious blacktop or pervious cement are substantially more expensive.
They're not up to par for Minnesota.
They aren't. Okay.
So far, but they're working on it. But it turns out asphalt and concrete are heading It's the highest quality.
Yeah. One of the things that makes a big difference on those, whether it's pervious concrete or porous asphalt, is how it's applied. And it takes different skills and different techniques in order to do it right. And not every contractor is able to do that.
Is that what?
Some claim they are.
Right, right.
Like you see test site, like test pavement, is that what that is then typically? There's like they do a resurfacing and it says test pavement area. Is that typically porous then, or is?
It can be all different kinds of things. You know that MnDOT's Minroads up by Monticello, where sometimes you kind of get directed off the road into a test site. They have both on that spot, and then they also have a separate track, which is their pavement test track, where a truck just drives around it for 8 hours a day. You know, guys who are on light duty and they can't go out working, but they can drive a truck. They just have to go drive around in a circle all day. And they have different types of porous pavement and different types of mixes. So that's what they're testing. They're testing different types of mixes. And it is very early to see how suitable that type of pavement is for those hard loads of truck traffic. a lot of the installations of porous pavement right now are in parking lots. So, they don't get a lot of load on them. So we don't really know what their useful life is going to be because we're not really subjecting them to a lot of loading and testing.
For example, out in Woodbury, they have on a county road, they collect a lot of the water from the road and they store it underground and then use it to water the golf course.
Mm-hmm.
And so you don't necessarily have to soak it in, you can just hang on to the water.
Right. Yep. That's another useful application of it. Let's move on.
Okay, so much like everybody else is saying, it's the retention practices that really have to be promoted. The downspout disconnect, the rain gardens, pushing green space around urban waterways to get that buffer zone so water just isn't blasting into the rivers. We also discussed identifying vacant urban lots that are totally impervious and repurposing them as green space.
Okay.
So that was one idea.
Any questions or comments on that?
Yeah, I read an interesting article a few months ago they were doing that in Cleveland, like with just vacant lots or turning into food.
Yeah, and the Trust for Public Land, and I think they have an office in the cities.
Mm-hmm.
They do a lot of work doing that.
They do work in the environment.
Yep, that's exactly what they do.
Yep. And you had a comment up here?
I was just, through the things we've been talking about, my mind keeps jumping to that new 8-acre park in downtown Minneapolis and
Mm-hmm.
wondering how that's going to be put together and what that might
That's a good question, isn't it?
from the dome
Yeah.
towards downtown.
The yard. You'd think that would be a really good spot for some innovative practices, and I don't think they're anywhere near thinking at that level yet, but it'll be interesting to see what happens. Let's go out to the last couple of groups so we can have our final slides here and get you out the door by 9.
We were, I think, on the same thread as pretty much everyone here about the limiting the flow, increasing retention and infiltration. But we were saying to reduce the flow is, I think, the most important, because even if you want to stabilize the stream bank, if you're going to have high velocity and super big events and everybody's water is just flushing down, your stabilization isn't really like as beneficial as it could be. So doing the green design, green roofs, collection, rain gardens, all these things that we know about. We were also discussing where the downspouts or the outlets are for the urban runoff. That, and then you had discussed Lake Harriet and Calhoun, that anytime there's a spout, we should have a slowing point so that it's not as fast into the stream. The plants that have the deeper roots, like the native species, I think in general they're obviously going to be beneficial anywhere that you plant them, but particularly on the stream sides in the riparian zones, because if you don't have the collection underground, you end up getting that erosion. Agricultural water should possibly be regulated like the rest of our water.
Good luck with that.
They're always in their own category, and their farmers are very important, and yes, we need their food, but I don't think that the farmers have incentives to build hedgerows and to build retention ponds on their properties where they might have a buffer, but they're not necessarily being as proactive about it. So if we had regulations on the agricultural water use, that would help, even though they're not directly the urbanized zone, but they are developed.
Well, and as we saw in the city of Davenport, that had a big impact on the stream running through the city.
Mm-hmm. So. Yep. And then some of the other things that we discussed were about developing sites. So, contractors come in and developers, and they don't necessarily design for site-specific, things. And like talking about Frank Lloyd Wright and these architects that are like being more sensitive to the landscape around it and being more aware of that, I think would definitely help. And then when they're doing construction, a lot of times they do kind of like guard off trees that are like historic trees or, you know, sensitive areas so the equipment doesn't get so close. But if we could even narrow that down more so that any of that big equipment was on like a very specific path and they didn't have free range of, you know, such a large area when they are developing a site, maybe. But that was about it.
Any questions or comments on those suggestions?
Unless
Yeah,
you have
I
more.
did. Also, you know, I was trying to think because all these ideas we were kind of looking at, and I was trying, since I don't have that great a memory, I was trying to think of a mantra like the reduce, reuse, and recycle thing. I was wondering if there was one for this. I was trying to come up with something, but I was thinking of like minimize imperviousness, slow and reuse the stormwater and prevent damage after the fact, erosion. But I was wondering, you probably in the business have some sort of mantra like that?
Knife-pierced cranium of famous Girl Scout. Kingdom, phylum, class, order, family, genus, species. No, I mean, I think the closest one to that is in the wetlands regulations, and that's avoid, minimize, mitigate. So the first thing that you're required to do is do everything you can to avoid impacts. If you can't entirely avoid them, then minimize impacts. And then the last thing is to mitigate them. So it's kind of similar. You know, if you can avoid all those bad things or minimize things like impervious surface. And if you do, you know, obviously, I mean, we have to have houses. We have to have some way to drive around. But if we can mitigate those impacts in some way, then maybe, I don't know. Maybe that's your role, is to come up with the knife-pierced cranium of famous Girl Scout of water resources. Huh? Slow it down, spread it out, soak it up. Yeah. It's no knife-pierced cranium, though. Yeah, they are, and they make lots of roots. So when you plant the live stakes, they shoot out a lot of roots, and those roots knit together. Yeah, you can just trim them. Yep. Yep. Yeah.
Do you know who introduced or who the progenitor of willows is?
No.
Alexander Pope, the poet.
Oh, really?
Yeah, Michael Pollan wrote about it in one of his books.
Oh. Okay.
All willows, older lineage.
Wow, I didn't know that. Wow, so I learned something today. One thing that struck me as we were going around the room is that an awful lot of the ideas that you had are things that can be accomplished by individuals or small groups of people. Doesn't necessarily take big actions or governmental actions. Some types of things do. Sometimes you have to go through those types of organizations or those types of regulations or those types of hoops. But a lot of those things can occur at the individual level. And I'm sure that you're all here going through this program because those are the kinds of things that you want to affect in the community. So what you've just written down here, you will in later parts of the program be learning how to do exactly those kinds of things and getting the tools that you need to go out there and make those things happen. So I'm going to wind down this evening just talking a little bit about climate change. And if you're a fan of Dr. Mark Seeley, and I'm sure most of you here are, you've probably already seen many of these slides. But I'm just going to throw them out here because we're thinking in context. We've just learned about things like precipitation depths and return frequencies and runoff and impervious surface and all those different things that go into how water moves around. And now, let's take a step back, and we talked about this earlier this evening, and think about how those kinds of things that we see changing in our climate, how that might have an impact on the amount of water that we have, how it how much of it becomes runoff, where it goes to, and what kind of effects that would have on the landscape. So Minnesota's average annual temperature has been on the upward trend. In the last 10 to 15 years, the slope of that trend has increased. So it's getting, the average annual temperature is increasing at a faster rate than it has been. We're getting warmer. The average minimum temperature, same kind of thing. The average minimum is getting hotter. In the last about 15 years worth of data has shown that it's getting hotter at a faster rate. Here's the Minnesota state averaged annual precipitation going back to 1890. You've got the scatter of the actual average annual precipitation. The line graph is the moving average, so it kind of smooths out the scatter and all that data. You've got some brackets there where you've got the middle there is the median, and then you've got the 25th and the 75th percentile up below and above it. And one thing to point out is that usually if you've got a median, the median means the middle, right? So if you've got a lot of annual variation, you should on average be above and below the median about an equal amount of time. So you'd have some dry years, you're going to have some wet years. If you look at the last 15 years, that average is always greater than the median. So the amount of average annual precipitation is going up, and it's going up at a faster rate than what it had been in the previous 110 years. It's getting hotter. The lows are getting higher, and we're getting more precipitation. We're also seeing more seasonality in precipitation trends. So we're getting more precipitation, and more of that precipitation is occurring at different times of year than it used to occur. So on these graphs, those green bulges are when we're getting precipitation for that quarter above the median, kind of the tannish are below the median. And you can see in winter, some years are high, some years are low. Spring, kind of the same thing. We're getting a little bit more in the spring than we have been. Summer is, kind of above and below, and you can see where the Dust Bowl years were, that big tan bulge there in the summer, down below the median. And then in the fall and winter, what's happened in the last 15 to 20 years? We're getting a whole lot more precipitation in the fall. So we're getting more precipitation, and it's coming in the fall. The last thing is we're seeing more and more days with dew points greater than 80. So the little red triangles there are locations that have had 10 or more days since 1996 where the dew point has been in excess of 80 degrees. 80 degrees is tropical. And the black dots are we've had at least one day. Look up there in the northwest corner of the state. We've had areas in the northwest corner of the state up there in the boreal forest where we've got dew points like it was tropical. We've got more water in the atmosphere. We've got a warmer atmosphere. What does that mean for our water resources? Well, here's a couple of things. First of all, if you've got warmer temperatures, you're going to get more evaporation, right? It's just got warmer air. You're going to lose more water. The plants are going to grow more vigorously, so they're going to be using more water. So they're going to be transpiring more, so you're going to get more ET. And then you can see that in the increasing number of days with dew points in the tropical level. What does that mean for our water resources and for our landscape? Some areas get drier. Some areas get more rain. All that rain's going somewhere. But we're also depleting things faster, especially over in the western part of the state, where we're getting closer to that line where the Great Plains start, where precipitation then is less than the annual evapotranspiration. Those areas are drying out faster. Our rain events are more intense, and we talked about that earlier when we were looking at hydrographs. We're getting more rain. We're getting rain events where the peak is higher, and those rain events are coming faster. So that hydrograph is squishing together, and it's raising up higher. with warmer winters, we've got less snow and less snowpack. Like I said, you know, we mostly focus on rain here in Minnesota. That doesn't mean we ignore snow. We need our snow melt in the spring, you know, to help fill up our wetlands, and especially if we happen to have had a dry fall, we need to replenish things. We need to replenish the aquifers. Snow, the melting snowpack does that. We've got warmer winters. We have less snow and less snowpack. Just heard something. I don't know if anybody else heard this. Isn't that Sierra Nevada, maybe? Where they have like 17% of their average snowpack? 12, something like that? We also have a longer growing season. Longer growing season may seem like a good thing, especially if you're a farmer. You know, you've got a chance to get in, you know, maybe you got 2 wheat crops that you can get in. Maybe you can get in, you know, more of something else, or you can get the crops in faster, and you maybe won't feel the impacts of a wet spring as you may have in the past because you've got a later fall. Longer growing season, more and more of our farmers are relying on irrigation to grow those really intensive crops because the commodity prices are so high. That means we've got more irrigation withdrawals from our groundwater. And we're not getting the snowpack to melt to replenish our groundwater. So our groundwater supply can be going down as well. And then the increase in water temperature. If you've just got generally warmer temperatures, and water temperature is influenced by the air temperature, you'll start seeing impacts in those cold water fisheries where you'll start losing some of the aquatic species that require a very, very cold groundwater replenished source of water. So that's some of the implications of these observations that we've been seeing in changes in climate, just in temperature and humidity and in the intensity of rainfall. So I'd like you to write this down in your book and think about this question between now and the next class. We can talk a little bit about it in the 5 minutes that we've got. But I'd like you to stop and think about this, not only what we've just talked about, but in terms of everything that we've talked about tonight. What can we do to minimize the impacts of a changing climate on our water resources? More intense rainfalls, warmer temperatures, more ET, groundwater withdrawals, less snowpack. And think big picture, what we can do as a society, but also what as individuals can do. Has everybody got that down? If not, the presentation will be loaded up and you'll be able to get back to it. So reflections and final thoughts. What did you learn? What was the takeaway from this evening? Pardon me? We waste a lot of water. We change where water goes to, right? Because we talked about at the very beginning about water as a cycle. If we were disrupting that cycle by the changes that we're making to the landscape. And that's going to have an impact on where we get our drinking water from, how we are able to grow our food, how we're able to enjoy our water resources. What was your takeaway from this evening? Go ahead.
My takeaway, I like that 70% is in the first thing. And then, again, we're a lot of people that are going to make maybe some small changes, and that's a huge impact.
That's a great point. That it seems like a small thing if we can just direct, an inch of runoff into a rain garden, but if everybody did it, that's 70% of the annual runoff. What else have we? What's something else that you've picked up? Go ahead.
So
And I didn't even bring up curve numbers.
But it's nice that the things that people can do on the different
Well, and I think what, you know, what we've identified, and as you went around, you talked in your small groups and went around the room, is that it's a complex system, but there are certain known things that you can do. And they're things that you have the ability to do. They're not difficult, infeasible scientific challenges. They're very feasible things that you can do.
Yeah, for example, one of the neighborhoods in Maplewood where they put in the whole living streets infrastructure has the same hydrology as it had before it was developed, so that they're soaking in the right amount of water and evaporating the right amount of it. So they also have a kind of a big park in there, so they have more space to work with. But it's not impossible to regain our previous functioning of our landscape. And with climate change, I think it's important for us to try to suck in as much water as we can into the ground because our aquifers are having trouble.
Now, the articles that you read before you came to this class, has any of the information that you've learned here tonight changed your perspective on the article that you read? In what way?
One was a 3D measuring of precipitation, or I think it's
Mm-hmm.
clouds even. But thinking about West Coast and Midwest, seeing how that information is valued.
Mm-hmm. Right. You know, we have different climates. We have different ecological zones within the country, and hydrology does vary depending on your unique characteristics. So, in the back. And that's a good point. And we don't often think about the groundwater impacts of what we're doing, whether it's fracking, whether it is ethanol production and withdrawals for ethanol production. All of our ethanol plants are just like the worst place possible for withdrawals from the aquifers. That's not where they ought to go. They're depleting the aquifers faster than it can be replenished. But that was not taken into account when those plants were sited. So, because you don't see it, that's right.
And we get our vegetables from California a lot too.
50% of produce comes from California, or will not be coming from California.
Don't you think that then goes to the subject of education in terms of, we're on a little microcosm here saying that we're going to do a grassroots thing by going out and trying to educate people about how locally our water is being affected, we're affecting our water. But in order for that to really take hold, don't we have to have a much broader view of how all water systems work across a sort of global environment? Because it's no different than trying to tell someone about a practice that works in our area that could be dealt with differently in another area, and the person over here is saying, yeah, well, we don't have to do that because.
Mm-hmm. We're not Phoenix. We have plenty of water. Right.
I just worry about being so limiting in that we're not looking at it as a much bigger picture, although I do realize that the product of this class has to be smaller scale.
Right. Like anything, I think it takes a crisis to get people to think differently. Lots of people think differently about both surface and groundwater since White Bear Lake has reached record low levels. That kind of thinking and that would never have happened without that crisis. It'll be the same thing in California. That Phoenix ran out of water. That's why Phoenix deals with its water in a very different way as far as recycling and reuse. And hopefully California, it will take this crisis for California to say, well, maybe we can learn something from Phoenix.
So do you think that the people who are living in the mountainous regions where they're dependent on snowpack for their water, not rainfall, do they have as clear of understanding? Do they just consider that our water is replenished by rainfall, or do they actually understand that their water is replenished by snowpack?
I think it was hard to say with generality, but I would guess that probably not. Earlier we were talking about montane forests, and one of the things that happens in a lot of developing countries has been that as development occurs, they go up into the mountains and harvest the timber for building and whatever, or for industrialization, for export. And then suddenly there's no water down in the valley because those trees are gone, because the trees were, by condensation, were providing the water for the valley. So, but they don't have the understanding to put that together. And it may be the same thing in some communities that are dependent on snowpack runoff. So, hopefully, we can educate people before it comes to a crisis, and that'll be your job. So I'm supposed to tell you that you have evaluations.
Yeah, please make sure you're turning your evaluations. If you don't have one, we have extras up here. And thank you, Diane.